About forces and interactions. And this is part one. We'll continue this next time, forces and interactions. Okay? So this is a new topic. Again, some of you may have seen this in a basic form, but I'm going to challenge you probably throughout. So I want everybody to pay attention. But before we do that, I want to introduce this actually with a little bit about where we ended last time. So last time we were talking about the Scottish hammer throw, and it was basically a heavy sphere at the end of a chain. You spin around. We talked about that circular motion. We'll see some of that again today. And then you throw this thing. And we all had the intuition that you want to throw it at about a 45-degree angle to get a maximum displacement, right? To get it as far as you can. And so how can you find this maximum range or horizontal distance traveled for this projectile given an initial velocity, right? So let's say I know the vector velocity that I start with, right? It's some angle, theta, from the plane, from the normal, from the floor, horizontal. And I know that speed, I know the magnitude of that vector. The question is, how far does it go? You see that this is kind of an important question. If you were in World War II, this would be a very important question. This was important to a lot of people, unfortunately, in World War II. But let's go through this problem. Here's the basic thing that I'm going to tell you right now. We're not going to talk about wind resistance when we talk about this example. We'll talk about wind resistance later. But what do you think would happen if I shot a metal projectile at a speed v, and I wanted to see how far it goes, but then I shot a ping pong ball at speed v? Which would go further? The metal sphere, right? The reason is that that ping pong ball will feel wind resistance. And when I say ideal, so this is the ideal trajectory for a projectile motion in 2D, this means that we've essentially ignored any wind resistance. Who's ever gone to the SRC and used one of those fan bikes? If you haven't, I dare you, okay? On those fan bikes, what they do, as you go faster, they get more resistive. Try doing this. I challenge all of you. Go to the SRC, get on one of the fan bikes. They're moving arms. There's a big fan blade in the wheel. Try to go 25 miles per hour. Then try to go 27 miles per hour. Then 29, 31, 33. By the time you get to 33, I guarantee you'll be almost done. Right? Wind resistance doesn't go linearly. It actually increases as the square of the velocity. So that thing basically gets more and more resistive very quickly as the square of the speed of that wheel. So in these problems, we're ignoring it. We're going to come back to wind resistance later. But here's how we do this. Remember we said the whole premise of our discussion last class was that the x direction and y direction motion was independent, but it ran simultaneously. And what that allows us to do is that if we want to find this displacement in the x direction, there was an initial velocity in the x direction, which we found by taking the component of that vector, and it traveled a time t. So we know that all of this whole projectile, right, this whole parabolic shape took a time t is just equal to the displacement over the velocity, right? The x and y motion move simultaneously, but independent of one another. And so what we can do is we can take that time in the x direction and plug it into our displacement for the y direction. Okay? What we get from that is a funny looking equation where the height, right, so the height at any time t, basically, or at any velocity that we're given, is equal to where it started. So that was my y equals 0. If I was standing, it was about a few feet off the ground. But then I get these terms, x and x squared. Okay? What was the shape of our trajectory? What did we call it? A parabola. If I have a parabolic trajectory, it means that I have a function that's dependent on the square of my independent variable. Which term in this is the parabolic term? Can you see it? I see some people. The second term is y equals x squared. This is the definition of a parabola, is that y equals x squared. Now, the other thing to notice is that it's a minus sign. So a normal parabolic function is shaped like a bowl. A negative parabolic function is just flipped upside down. And so if you plot this thing, you get exactly what we said. You see that the displacement in y as a function of x forms this very well-defined parabolic shape. Okay? And it's coming from this x squared term, where there's another term here, linear in x. Okay? Here's a quick question, and I'll test you now, and then we'll see if this is true. How do I make this right here, this term, as close to 1 as possible? How do I make that, this linear x term, how do I make it as close to 1x as possible? If I take the ratio of two velocities, how do I get that ratio to be 1? I make them the same, okay? So what this first term, just as an intuition, this is how a mathematician would look at this, is to say, this term becomes order 1 when the x and y component of my velocity are the same. So my x component, my y component and x component of this initial velocity are identical. What angle would you guess the vector velocity has to be to have two equal components? It has to be about 45. We're going to see it in a second, but this actually gives us a clue as to when to maximize this function. So here's our question. I'm going to work through it step by step so you have this in your notes, but you'll also be able to work out some of the steps for yourself. How far has an ideal projectile gone horizontally when it returns to its initial height? This equation now allows us to say, if I want to come back to y equals 0, how far did I go? What value of x did I try? And you see that this is actually pretty straightforward. If I set my y value equal to the initial y value, y0, I can solve for x. This is the part I want you to go home and do. Okay? So solve for x with this equation by plugging in y equals y0. Does everybody remember? Well, I'll let you test and we'll come back to it next time. How would you solve this? There's a very special formula that teaches you how to solve this. Have you heard of the Quadratic Formula? Okay? Oh no. We're going to review it. This is the solution to the Quadratic Formula. We're going to come back to this. You'll see it in the discussion section. You'll see it on the exam. When I solve this, wait, let me finish. If I work through this, you'll see the solution next time if you don't trust me. I get this thing, I'm going to label it as range, right? So this is called the range equation. How far do I go in the x direction? The answer comes out to this very neat little answer. It says the initial speed squared, so the magnitude of my initial speed vector, times sine of 2 theta, where theta is this angle from the horizontal, divided by some constant, g, which is a number, 9.8 meters per second squared. Now we can look at this equation and see this function is maximum when 2 theta is equal to 90 degrees. When is the sine function maximum? Let me draw the sine function just to remind you. Here's theta. Here's the sine of theta. What does the sine of theta look like as a function of theta? I see people doing it. It has two half wavelengths. It forms what we call a sinusoid. Okay? What is the angle equivalent to pi radians? How many degrees? 180. Okay? What about 2 pi? By extension. Okay, we don't call it like an extreme snowboarder. They don't use radians. They use degrees. They don't call it a 2 pi or an 8 pi. Anyway, never mind. So this thing looks like a wave function. This is a sine function. If I look at my solution, where is this function at its maximum? Just look at the board. Where is this function at its maximum? Pi over 2. What is the angle measure of pi over 2? Degrees. It's 90 degrees. Okay? So this equation gives me the maximum range when the sine function gives me an argument 2 theta is equal to 90 degrees. Or in other words, that the angle from the horizontal is 45 degrees. Okay? So this range equation gives us exactly what our intuition was. And 45 degrees gave us the maximum range. But what it also says, when I have a velocity vector, v naught, here's how I've drawn it in the top right, if I take its x and y component at 45 degrees, I get that both components are equal in magnitude, right? That's the only angle where the x and y component will be equal in magnitude, is at 45 degrees. And that's what we saw in that previous equation. So here's some work to do on your own. You can check a couple of things. You can check that when I plug in 90 degrees, I get x equals 0, right? That should work, because you're giving both x equals 0 and then range. But I should also see that when theta equals 0, I get x equals 0. Okay? So you should see that this function gives you a sanity check. When I go x equals 0, I should see 0 range. When I go out to r range, or the furthest distance, that's happening at 45. Now the other thing to check in here, and you should do this, is the units, or the dimensions of your answer. And this will come up in exam after exam. You will sometimes be given answers on your exam in a multiple choice format where the dimensions aren't even correct. If you can look at the dimensions, so the units of range, what should the units of range be, or distance? Meters. If I give you an answer that says 12 meters per second, you immediately know that it's wrong. The units have to be correct. Now the other thing to show, and you can work on this, is that the projectile's maximum height, how far up does it go to go through this parabolic shape, is v naught squared sine squared of theta over 2g. And you can do it with this equation. So just to get a feel for how this equation works, I want you to work through this on your own. It should only take you a few minutes. And there's a pretty interesting thing about this function, and you'll see this in your notes, but you don't have to worry too much about it. Yeah?
I just want to clarify, when you define the question mark, the variable r, would that be the same as the shape x, right?
Exactly. We just gave it the name range.
Okay, so we're just safety.
You're just finding delta x. The reason I use r is that they call this the range equation, because you're asked what is the range of your artillery fire, or what is the range of my spring-loaded ball fire. So it's delta x. Okay, so one more thing to say is that this function has a funny kind of shape to it that's a symmetric parabola, and so there are actually two specific angles that will give you similar answers in this. And so you can stare at this and dissect it. I won't test you on this piece. It's just kind of a curiosity of the range equation. Okay, so let's move on. That was just kind of finishing up what we had in intuition. For now you have in front of you, I want you to work through those steps on your own. It should just take you a few minutes. So here are today's goals. We're going to introduce force. And we're going to work with force for the next 2 to 2.5 weeks. So it will get more and more and more challenging, but we're going to kind of leverage what we've done already. So we're going to define force, we're going to characterize some of its basic properties, and we're going to determine what forces do. Okay? The other thing we're going to talk about is a whole bunch of examples of force. We're going to introduce some of them, and we're going to talk about these most important piece of this is Newton's laws of motion. And I'm going to introduce these laws now, and then we're going to take the next 2.5 weeks to really understand. It's not an easy topic, so we're going to take our time. So we got our first question. Let me deliver this one. It's a straightforward one. It's just to kind of gauge previous knowledge or whether you're reading. And this question is, what can forces do? What does it mean to say what can forces do? What do they do? So here are the answers. A force can push, pull, stretch, compress, or shear. B, a force mediates an interaction between two objects. Or a force can cause or prevent an acceleration. And then the last one is 2 are correct, but not all of them, or all of them are correct. Okay? So go ahead and see which of these. Take about 30 seconds. From what you know, what you've read, if you don't know the answer, you probably haven't read. If you haven't read, start reading. It's going to benefit you quite a bit. Okay, take about 5 more seconds. Keep going. I've only got about 100. Keep going. 2, 1. Okay. Here's what I'm seeing. Wait, this is actually really interesting. I wish I could show you this in time. The people that answered in the first 30 seconds, okay, 95% of those people got it right. Okay? So if you've answered in the first 10, 20, 30 seconds, most of you got it right. Okay? As we took longer and longer, that number shrank. It was about 95%, it's now 64% got the correct answer. This is probably the divide. There are people who are staying on top of the reading, and there are people who are probably just being pretty relaxed about it. If you stay on top of the reading, you're going to have a much better time coming to lecture. You're going to understand a lot more. So let's just stare at the other answers. So here's what I got. 28% of you said D, which was 2. 65% of you said it was E, that it was all of the above. The correct answer is that it is all of the above, in fact. Okay? We're going to talk about this. We're going to introduce Newton's laws. A force can do any of these. It can push, it can pull, it can stretch, it can compress, it can shear. A force, this is the most important part of this, actually, is that a force, by definition, mediates an interaction between two objects. And we're going to come to learn this very, very agonizingly carefully in this class, that we always have to have two objects. And C, a force can cause or prevent an acceleration. Who's heard of the basic form of Newton's law? What is it? F equals ma, mass times acceleration. That answers this one already, just from what you've probably heard watching YouTube. If you just were a computer learning from YouTube, you'd already know F equals ma. Okay, here's a good one. This is going to test what we know so far, and we're going to use this to understand forces. Here's what I'm going to do. I'm going to take this tether ball. Imagine you're looking down from the roof at me spinning this ball. So I'm Professor Pete. I spin a tether ball over my head. If the string suddenly snapped at some point along that trajectory, which path best represents the ball's subsequent motion? So imagine, this is the motion. You're looking down on me, and then suddenly, the string gets snapped. Which direction of motion will this ball continue to travel? Okay. Think about it. First, think about it on your own. We'll see how it goes. It's actually, often people get tricked up by this one. So take your time, think of it on your own. Take about 30 seconds to get an answer in. Okay, so try to get some answers in about 10 seconds, just on your own, and then we'll come back to it. I want to see how we do just on our own. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2. Okay, stop. Okay, this is actually pretty good. So about 65% of you got the same answer and got the correct answer. So here's what we're going to do. I want to think about what we know so far. What did we say about circular motion last time? We spin this ball around. Which direction is the acceleration in this problem? Towards the center. Okay? So what do we call this acceleration? Centripetal, not centrifugal. Okay? Centrifugal is a fake force. Centripetal is a real one. Okay? So the acceleration is inward. What would happen if that acceleration was suddenly gone? What would happen to the ball? It would fly off in some random direction, right? So that acceleration is what's pulling it inward to stay in this circle. Did you ever hear this statement that an object in motion tends to stay in motion unless otherwise directed? If I suddenly had this ball let go from the string with some speed, it would stay at that speed forever if we were out in deep space. Okay? Now, let's think about another thing we learned about circular motion, or a trajectory. At any given instant in time, which direction is the velocity point? I heard it, tangent to the trajectory. Okay? Look at our answers. Take another 30 seconds. Use those two pieces of information and see if you can change your answer. So find out. I'm not going to tell you what the correct answer was yet, but if you had it with confidence, talk to the people around you, see if you can convince them, or see if they convince you. Okay, take about 15 more seconds. So I already got most of you in. Again, remember, this is over my head, it's spinning.
Okay, 5 more seconds. There's a couple left. Okay, stop. This is good. So either people are very good at convincing others, or you maybe have converged on an answer. You had 63% answered C the first time. 87% answered C the second time. It turns out C is exactly the right answer, right? This one is actually a bit tricky. There's a good reason that people had different answers. But what is it going to do? When I cut this string, it's moving at a tangent velocity, and it no longer has this acceleration pulling it in towards the center. So it's just going to shoot in that direction. Answer C. Okay, good. Let's go to one more. Which best represents the force vector immediately before the string was cut? Okay? Take your time. You can talk to friends right away on this one. Talk to the people around you. Which best represents the force vector immediately before this goes? So again, it's over my head. Where's the force that's pulling this motion? Take about 30 more seconds, but talk to your neighbors. The same neighbors that convinced you last time might be right this time.
Oh.
Okay, 5 or 7 more seconds. Get your answers in. It looks like most of you have it. Okay, I'm going to stop. Here's what I got. 68 of almost 70% of you said the answer was C. The arrow pointed to the left. Okay? What was the acceleration in this problem to keep that ball going in a circle? To the left. What is the force that's pulling it to stay in that circle? Do you know? We're going to talk about it really detailed, but what's the force acting on the ball that keeps it in that circle? Okay, well, she's saying going around. That's not quite it, but it's close. Here's what it is, and we're going to come back to this. It's really simple if you just look at the problem. The force pulling the ball is the force of the rope pulling the ball, right? As simple as you can look at that picture, you can answer this question. We're going to practice this a lot. The force pulling that ball is to the left, and it's the force of rope on ball. Does that make sense? How many objects are involved in the force? 2. There's a force of the rope on the ball. We're going to come back to this in a minute. Let's do one more. So 68% of you got it right. The force is in the direction of the acceleration. What did we say with Newton's law? That the force basically imparts an acceleration. Let's do one more. Which best represents the force vector immediately after? Some of you probably could see this coming. You have 4 choices: up, right, left, none of the above. Talk to the people around you. Again, remember, this is over my head. I'm spinning this ball around. I cut the string. What's the force immediately after that thread is cut? By the way, the Vikings used to use the phrase "thread is cut" to mean you were slain in battle. So, just a little piece of trivia. Now remember, you're looking down on the ball. Okay, take about 15 more seconds. Okay, 5 more seconds. Okay, I'm going to stop. Oh, right at the last second. Okay, here's what I got. So 60% of you said the answer was A, that it was up in this diagram. Okay? What is the force pushing that ball up in this diagram? Or in other words, when I spin this above my head, what is the force that's going to continue pushing that ball to a tangent of the curve? Right? You all said that the velocity was up. Right? You said the velocity was up. It was tangent to the curve. We did all of that. What's the force pushing it? There is no force pushing it. Okay? When I let go of this ball, we're going to learn really carefully. Objects in motion tend to stay in motion unless acted on by another force. If I let this ball, what's going to happen in time? It's going to have a velocity, say, this way, and then in real space, it's going to start to drop due to gravity. What is the force acting on the ball in this problem? Down, and what's the acceleration? Is that any of those vectors down? Not at all. What's the right answer? None of the above. Okay? This always tricks everybody. This is on purpose. But it turns out that 24% of you actually got it. So I saw some little under the table high fives between a couple people. I saw them. I could see it. This is good. We're going to now explain why all of these are true. I think you now have an intuition for the first couple, but now we're going to come to this one. This one's tricky. Objects that have a speed, a velocity that remains constant because there's no acceleration, that means there is no force acting on it. Okay? By Newton's laws, we'll see that that's the case. So what exactly is a force? I wanted you to go through these exercises to connect it to vectors because we'll use them a lot in this case. But what is a force? A force is simply a push or a pull. And we'll talk about many examples. So a force is how we use it. The language is a force. Okay? It's a very specific action. This allows us to talk about 2 or 3 individual forces. Remember in this tether ball, I said it was the force of the rope on the ball. That's a very specific force. We sometimes call that tension, and we'll see that a little later. A force always acts on an object. It basically is to push or pull that is applied to something. And you have to specify what that something is. When we start applying this to complicated objects, you have to keep track of which force is acting on which object. A force requires an agent, right? This is the two-body thing that I said. There is a distinct cause of the force. I was pulling on the rope. The force of my hand on the rope was equal to the tension in the rope. The force of the rope on the ball was also equal to the tension in the rope. You see that there's an agent, me, and there's an object, the rope. But then there's another agent, the rope, acting on the ball, the object. So there will always be in what we call an interaction pair, and we'll come back to this in gory detail. The force is in general a vector, and this is why we work with vectors so much and continue. There are different levels of force, right? I can push you really hard, or I can give you a gentle push. That's the magnitude. But then also, I can push you to the left or the right or up or down, etc. They have a direction, and we need both of these to know what the force and how it acts. Okay? That's why we use vectors. This is why we've introduced vectors in 2D motion. Now, here's where it gets a little tricky. In this course, we almost exclusively use contact forces because they're easy to have an intuition for. What is the one force that we will use here? We've already talked a lot about it, that is not a contact force. Gravity, right? Gravity is the force of Earth on me, right? The gravity is basically pulling me toward the center of Earth's mass. Okay? It is the force of Earth on me. We call it a non-contact force because even if I was out in space, I have a force on me from the mass at the center of the Earth. That's the basic center of mass of our planet. It doesn't require contact. In fact, what's keeping me from being pulled into the center of the Earth? What is it? The ground. But what's the force? It's the force of my legs on the ground. Okay? We're going to give this a name in a couple minutes, and you probably have seen some of this before. Normally, you can have these things that are not contact forces. They're called long-range forces. There are several of them. One is the magnetic field, or the magnetic force. I can take two magnets. If I put the two north ends and I try to force them together, I feel a force, even though they're not in contact. Most of what we'll do in this class is contact force, except we'll also do gravity. Gravity is a pretty general and easy one to deal with. Now, here's the key thing that I want you to remember in everything that we do from now on. When we talk about a force, we always have a force of object A acting on object B. Always. If you solve a problem and you find that you can't figure out which object is A and which object is B, then the force that you're drawing or thinking about doesn't make sense. There will always be an agent and an object when we talk about force. We will see lots of examples, including today. And this slide is the most important slide. We'll see this every day for the next 5 or 6 lectures. These are the statements of Newton's law. We're going to dissect them and understand them. Right now, they won't make too much sense, or they may make a little bit of sense, but not completely. But we're going to understand them one at a time. So here's Newton's first law, sometimes called the law of inertia. Here's what it says. In an inertial reference frame, a body on which zero net force acts either remains at rest or moves with constant velocity v in a straight line. This would be the natural equilibrium state of a body that is free from external force. If I put a little metal sphere out in space and I threw it, it would just travel at a constant speed without force. If it came near a planet, what would happen? It would steer, it would be forced toward that planet because it has mass. When I have zero acceleration in the system, by definition, I will have constant velocity, right? We learned this in motion. Zero acceleration means uniform motion or constant velocity. The velocity is not changing. By extension, we call this an inertial reference. Okay, here's Newton's second law. We're going to get more complicated. In an inertial reference frame, for every body, every object in the system, it could be all of us, it could be a desk, a chair, all of the things, the sum of all forces acting on that one object is equal to the mass of the object times its acceleration. This one you've heard about. Remember from kinematics that we define acceleration as the change in velocity with time. Do you remember we took displacement time graphs and I told you to find the velocity? And then you took a velocity time graph and then I told you to find the acceleration? If I gave you a displacement time graph, could you find the force on the object? Absolutely you can. The force is equal to mass times the acceleration. You can find the acceleration time graph from a displacement or velocity time graph. You can find the magnitude of the force on that object. You'll see this in discussion section. The other way to write this is that if there's an acceleration in the system, if I know, coming back to this ball, we said, which direction was the acceleration? Towards the center, centripetal acceleration. Is there a force acting on this ball? Absolutely, it's toward the center of the circle. If I cut the string, I take that acceleration away, and there's no force acting on the ball besides gravity. So if I know there's an acceleration in the system, there must be force acting on these objects. And this is the most important one, the most tricky, and this is the one that we'll study a lot after the exam, is that force is the agent of an interaction between two bodies. We always take, even if I have a whole bunch of objects, 30 objects, I take any two and I ask, what is the force of A on B? And what I find is that each interaction between these two objects, A and B, consists of what we call an interaction pair of third law partner forces. If I push on this bench, okay, is it accelerated? No. Its velocity is 0, its acceleration is 0. I have a force of me on bench. There is an equal and opposite force of bench on me. What if I took away the bench, the force of bench on me? What would happen to me? I would fall. I would accelerate. Okay? So in Newton's third law, what it says is that the force of B on A, so the force of bench on me, is equal and opposite, see there's a minus sign, to the force of me on bench. This is always going to be holding true in any reference frame, inertial or not. Okay? This is the one that allows us to solve these problems in a very, very nice way, and you'll see that this comes up quite a lot. So let's take the first one. This is the first Newton's law, the law of inertia. A body on which 0 net force acts either remains at rest or moves with constant velocity v in a straight line. And this is what we would say is the natural equilibrium state. Here is an object at rest in static equilibrium. Luckily, he's looking the wrong way because skateboarding across the front side of MS&E, there's a bunch of kids, and they're moving at constant velocity. Their acceleration is also 0. This skateboarder is just moving at a constant velocity. Both of these cases, v equals 0, a equals 0, or constant velocity but 0 acceleration, these are both in their natural equilibrium state. We give these two different names. We say that this one is in static equilibrium, meaning it's held still. This one is in dynamic equilibrium. Okay? So the sum of forces adding up on this skateboarder is still 0 because he doesn't accelerate. Do you see the connection? This is what Newton's law told us. If I basically say, number 2, acceleration, if I say that the acceleration is 0, it means the sum of forces on that object is also 0. And that's exactly what we said here. He has a constant velocity, no acceleration. He's in equilibrium. So what do we think about attributes? When we think about different attributes of a force, and we're going to do lots of demos, we'll see lots of things, but I just want to move through a lot of different examples. Forces are either contact forces, meaning two things are in contact, a push or a pull, or long-range forces, and these are what we would call force fields or field forces, gravity, electromagnetic force, and several others. The only long-range force that we will deal with in this course is going to be gravity. Right? For simplicity, we're not going to do E and M. You'll do that later on in the 2 series. Here's a very simple one. If I take a spring and mount it on a wall and I attach a handle to it, there's a force of my hand on the handle. There's a force of the handle on the spring. And there's a force of the spring on the wall. You see that these are all in contact, right? Each of these bodies that make up this complicated system are in contact. The only one we'll talk about is this one, which is gravity. When I have two masses at some distance, and they are some magnitude, they attract. Okay? Here's the hard part. We're going to practice this today and we'll move on. A force is a vector. Right? This is why we've been working with vectors so much. I'm preparing you for this. The force has to have a magnitude and a direction. Let's say that there were two people. This is looking down on a box. Remember when we solve problems, what's the first step we do always when we try to solve a problem? Draw a picture. Okay? We try to pretend what's going on by using a picture. Look at this thing. What would happen if this person was pulling in the south direction, but this box is laying on the desk, and the other person is pulling at this corner? What would happen to this object? It would go, right? It would twist and be pulled. You would hear it scrape across the table. This is a picture caught at a moment in time. Most physics problems will ask you, how will this object accelerate with these two forces? So when you draw these pictures, the first thing you do, you draw and you imagine, how is this thing going to move when those forces are applied? Here's where we will see it here, is that these are vector forces. First of all, I can say, this is the force of person 1 on the box. I'll call it F1 and give it a vector of direction and magnitude. This is the force of person 2 on the box. I give it a direction and magnitude. If I sum all the forces, remember Newton's law said that the acceleration is equal to the sum of all forces, do you remember how to add vectors? We take this one, and then there's Samantha's law, which is you separate them and you draw it over here, and then put it down and you get the sum, right? So the sum on this particular case, the total force or the net force acting on this box is the vector sum of these two forces. Let's try one. 2 of 3, wait, this is a tricky one, so think carefully. Get your pencils out and draw. 2 of 3 forces exerted on an object are shown. There's one force acting on this. We are trying to figure out which direction the magnitude is. The net force points directly to the left. So I have 3 forces. I know that the net force is straight to the left. Which is the missing third force? Okay. Try to use logic. Talk to the people around you. You can draw it and get the answer exactly right if you remember how to add vectors, and if you think about what would happen if you pulled on an object with these particular forces. What force do I need to have the net force point directly to the left? So take another minute. I'm going to draw the situation just so we can get started. So one way to approach this problem as you're sitting here, if you look at all of these vectors and think about how it would accelerate if I applied those forces, you have to ask, would it accelerate exactly and only left? Because that's the sum of forces. So think about that. Just intuit from how the object would accelerate which direction this has to be. Take about 30 more seconds. Okay, 10 more seconds. I have most of the responses in. There they come. Okay, 5, 3, 1, 0. Okay, good. This is really promising. 78% of you said that the answer was C, down and to the left. Can somebody tell me how you came to that answer? There's several ways to do it. Can somebody tell me their intuition? You guessed, right? You rolled a die on the table and said, see it is. Okay? Let's think about it for a second. We're going to do one more, but let's think. Let's do it one way, which is, let's just think of what would happen. If I applied a force, A, right, up and to the left, what would happen to this object if I applied a force this way? I'll call it A. How would it be accelerated? I have a force to the right. I have a contribution to the right from this one. But what about the y direction? What's the net force in the y direction? It's up. This one would accelerate up. Okay? We're going to do this more rigorously in a second. What about B? Let's look at B. B says straight to the left. If I had a force, I'll draw it here as B. Forget about A. What about this one? Well, how's it going to accelerate? Up again. That can't happen. It has to go exactly to the right. How do we compensate for that upward pull coming from F1? More downward, which is the only one that can do it, that can pull both left and down. It's C. Okay? Now, let's do the next problem. So 78% of you got that. That's good. Let's do the next one to try to do it quantitatively. We'll come back to this one next time. Let's do this last one. Again, work with the people beside you. Do this quantitatively now. Draw your vectors, sum them up, and answer this question. This is a good one. This is a really good test question. Two forces of magnitude of 10 newtons sum to a resultant force of 10 newtons. What is the angle between these two forces? This is a really good test question. It's getting better every second. I've got another minute or so. Now, here's what I would say. Draw it really carefully, and then answer the question. Super, super careful with the precision of an experimental physicist. Okay, I'm going to stop in 5 seconds. I want to go through it. Shh. Get your answers in. 5 or 7 seconds. Okay, I'm going to stop. Shh. Here's what I got. So 45%, almost half of you, this was the largest number of any answer, got exactly the wrong answer. Okay? Let me go through it. We're going to come back to this on Wednesday. Watch. How do I add these two vectors? There's Samantha rule. I separate them out. Then I redraw them. Let's move this one to here. What is the addition of those two vectors look like? What does it look like? Down. Good. So from the end of this one to the tip, and this one is 10 newtons. So, this triangle has 3 sides. What are the angles inside the triangle? Okay, 60. Wow. Here's the kicker. When I asked the question, I said, what is the angle between the two forces drawn? This triangle is 60 degrees. What is the angle between those two vectors? 120 degrees. Perfect exam problem.